Welcome back, stats enthusiasts. We are now in Unit 9, which is all about inference for slope regression. We're going to be covering 3 sets of notes in this unit, and you have reached the first video in this series titled Notes 1, Sampling Distributions for Slopes and Confidence Intervals for Slopes. We're going to go over both of them today. We're going to talk about creating a confidence interval for a slope, and in order to do that, we need a sampling distribution for a slope. We're going to talk about conditions required for this type of inference and review a lot of the material that we have already covered dealing with least squares regression lines. So if you're ready, go ahead and grab your notes and get ready to dive into the material. So we're going to take what we already know about least squares regression and expand on it in this unit. So first, let's start with the big picture here. When we have 2 quantitative variables that we are trying to observe a linear relationship between, we can create this what's called ideal linear relationship. And it's described with what's called the population regression line. And that's going to be mu sub y equals alpha plus beta times x. Now, mu sub y represents the mean value of the response variable y for any given value of x. And then alpha represents the population y-intercept, and beta represents the population slope. So we're under the impression that there is a true population line that we can draw between 2 sets of data, right? This is the ideal, one could almost say theoretical, okay? Now, the reason we have this is because we can observe a linear relationship. That was what Unit 2 was all about, right? Where we created a sample regression line, y hat equals a plus bx, where a was the slope and a was the y-intercept and b was our slope. Now, we created this for different sets of data. So let's think about the activity where we had height versus arm span. We created a linear relationship between height and arm span. But we said that wasn't that was just a sample regression line, right? That wasn't the ideal. The ideal that Vitruvius said was that y equals x. That is the true population regression line based on his theory. But we came up with a sample regression line that described the data we have at hand. If we took many least squares regression lines of the same size from the same population. So let's say we did it for another class and another class and another class. We come up with different sample regression lines based on our data. And if we put all of those sample regression lines together, we can create a sampling distribution. And specifically, we're going to look at slope. There is inference for our y-intercept that we could do, but we're not going to touch that in AP statistics. We are going to look specifically at slope. So if we took all of the slopes from all of those different least squares regression lines and put them together, we create our sampling distribution. So the sampling distribution is based on, again, bivariate population data, and it has a given slope beta. So that, again, that's our population slope. Again, if we're looking at our Vitruvian man activity, Vitruvius said the height of a man is equal to his arm span, and that slope, that true population slope, would be beta equals 1. But through all of our sample least squares regression lines, we saw that we never really got a true slope of 1. It was always a little bit off. So that's the idea between the ideal and what we expect in our population for the ideal and what we get maybe using sample data. So the sampling distribution takes all of those slopes and put them together. So in our population, we have a given slope beta. We have the standard deviation of residuals sigma and a standard deviation value of x values sigma sub x. Okay, so these are all population data values because we're using those Greek symbols to describe them. If we take all sample sizes of n and compute the slope of each of those, you get a sampling distribution, right? We're putting all of the slopes together. The shape is going to be approximately normal. The mean, we say mu sub b, is going to be equal to beta, our population slope. And then the standard deviation is calculated a little bit differently, is going to be sigma over the sigma sub x, which again is the standard deviation of x values, times the square root of n. So just to kind of recap what each of those are in that formula, again, we're working with our population data when we use sigma there. And that's going to be the sampling distribution for the slope of a least squares regression line. Now, what can we do with the sampling distribution? Well, once we have a sampling distribution and confirm that we have met conditions to create a sampling distribution, we can begin to ask and answer our inference questions. For example, is there a linear relationship between X and Y in the population, or could the pattern we see just happen by chance? In the population, how much will the predicted value of Y change for each increase of 1 unit in X? Okay. So we're going to be answering these questions using confidence intervals and hypothesis testing. Now, in order to perform inference, of course, we have conditions. And the conditions for regression inference are going to be different than some of the stuff we've seen for proportions and for means. The first condition is that X and Y have to have a linear relationship, right? So you have to check to make sure that the scatter plot between X and Y can be described by a line. Remember that you don't want to just rely on correlation for this condition because correlation can be deceiving in some instances. You want to have a visual confirmation that, yes, you can see a linear pattern between X and Y. Our next condition, we want to make sure that we have independence met. So if we are sampling without replacement, we want to check the 10% condition to make sure that N is less than 10% of our population size. Now, if we're not sampling without replacement, if we have an experiment of some kind, in a well-designed experiment, independence is going to be there. So we don't have to check the 10% condition for that. That is very similar to what we've done with other inference procedures. Normal. Now, when we talk about normal, we mean that when X is fixed, your Y values follow a normal distribution for each fixed value of X. Now, the way we check this condition is to make a histogram of the residuals and make sure it looks approximately normal. Okay. Now, making the histogram, when you look at it, if it's approximately normal, perfect. It meets that condition. A lot of the times it won't necessarily appear approximately normal because we will be working with smaller sets of data. So if you're working with smaller sets of data, you want to make sure that there's really just no outliers or strong skewness. Okay. So even if it doesn't look approximately normal, as long as there's no outliers or strong skewness, we can say, okay, that's it. The condition is satisfied because we are working with such small values of N. If the graph does have outliers or strong skewness present, we need to make sure that N is larger than 30. And hopefully that sounds familiar for you because that is the central limit theorem coming in strong again. As long as N is larger than 30, basically our histogram of residuals can kind of look like whatever it wants to look like. The central limit theorem tells us that it still will be approximately normal. Okay. Now, equal standard deviations. This is a new one. It's kind of a weird one. It basically says the standard deviations of residuals doesn't vary with X. And the easy way to check this that we've already seen is to make a residual plot and make sure that there is a random pattern. So we've worked with residual plots before. We've seen instances where it could appear a residual plot shows non-normality. So if there's gaps, fanning, clustering, any sort of pattern on a residual plot, then this condition is not met. We just want that random pattern that we've always seen in a residual plot. And finally, the last condition, can you believe there's 5 of these? The last condition is random. We have to make sure that we took a random sample or we had random assignment in an experiment. Now there's 5 conditions, which is a lot. And I've ordered them this way because we do have a little bit of an acronym to remember them. Together, the acronym is LINER. So we have LINER to help you remember what those conditions are. So when you're creating a confidence interval or running a significance test, you can make sure that you hit on all of those conditions. Okay. So let's talk about a confidence interval in this section of notes. We can create a C% confidence interval to estimate the true population slope of the regression line with this formula. It is going to be the same formula that we've seen with other confidence intervals. It's our point estimate plus or minus our critical value times the standard deviation, okay? So our point estimate here is going to be B. Now, B is the slope of our regression equation, our sample regression equation. T star is going to be our familiar critical value, and then we have our standard error, which I'll explain more about in a moment. The change here to calculate T star, we are using a T distribution to calculate this, but our degrees of freedom are n minus 2. And you can remember that just because we have two variables is the easiest way to remember that. We did degrees of freedom n minus 1 when we were working with one variable, like the single mean. We're going to do n minus 2 for this confidence interval here. So a lot of this is going to sound familiar, right? T star has C% of the area between negative T star and positive T star in the T distribution. B is our point estimate, and that's going to be the slope we get from our sample data. Now, SE sub B, okay, what that stands for is standard error of the slope. So we went over in our sampling distribution, we had our standard deviation for our sampling distribution equal to sigma over sigma x times root n. So that's, again, our population, using population data to create our sampling distribution, the true sampling distribution. Now, of course, we don't have population data. So instead, we use the sample, S represents the standard deviation of the residuals. S sub x is the standard deviation of the x values, and both of these are going to come from sample data. So remember, when we use sample data, then we call it the standard error because there is going to be some variation from sample to sample. So that's why it's called the standard error of slope, is because we're getting S and S sub x through sample data. And then the n minus 1 is going to be underneath the square root now, okay? And our interpretation is the same as it's always been as well. We are C% confident that the true slope of the regression line lies between blank and blank. And you put some context to that, okay? So we're going to do an example of this. So I have a lot of information I'm going to give you up front, and then we're going to do our 4-step process using our 4 C's to actually construct this confidence interval completely. When you're looking at the AP exam, they do give you a lot of information in order to perform a inference for a confidence interval for B, just because you do need a lot of information, especially for those conditions. So here's the example, and let's go through the data we're given. So it says the data below was obtained from 15 randomly selected large school districts from around the nation. It shows what their average teacher salary is and how much they spend per student, or what's called their per pupil expenditure. So the data is actually in table form. We have it right there. And we can see that a scatter plot was already created for us with a line, a least squares regression line going through it. The next pieces of information we're given is all of this, what's called summary data, right? We're given a residual plot right here. And then notice how we're given a histogram. And on the x-axis, we have residuals. Okay? So this is the histogram of the residuals from our data values. So each residual, like here, this residual is about positive 2000, it looks like. So that's going to be probably this one data value here. Okay? So we take all of those residuals and we plot them as a histogram. So that's why we have negative residuals here, because those represent the points that fall below the least squares regression line with those negative residuals. And then we have positive residuals. So we're given all of this information up front, which is great. We'll talk about more in the homework and some of the other sections of notes how we might find these using our calculator. But on the AP exam, they give a lot of this to us up front because it is a little bit more labor intensive to find these using your calculator. So we have all of this information. It's up to us to digest it and come up with a confidence interval for B. So it says specifically, construct and interpret a 95% confidence interval for the slope of the population regression line. What type of relationship does this interval suggest, and explain it? So our 4 C's, right? We want to communicate, check conditions, calculate, and conclude. for this 4-step process. So communicate, we want to state the parameter of interest in the context of the problem. So our parameter of interest is going to be, what are we creating the confidence interval for? Well, that's going to be slope. And it's going to be beta because we're using population. That's our parameter, is beta. And it represents the true population slope between the average teacher's salary and the amount of money spent per student. So that's why I have that scatter plot kind of there again, so you can see we're looking for the true population slope between average teacher salary and the amount of money spent per student. This is also a place where we found like T-star, if you wanted to find T-star here, and how it relates to 95% confidence interval. But here in this part, I'm just going to put the communicate. I'll save T-star for the calculate piece. Next is conditions. We want to check our 5 conditions and see if they are met and see if we can perform inference about them. Now, remember when checking conditions for a inference procedure, and this goes for all inference procedures in AP statistics, you want to say if they are met, and if they are, perfect. Usually most of them are. But if there ever is one that is not met, and we're actually going to see an example of that here in a moment. If there's ever one that is not met, we do want to draw attention to it. Don't just, say it's met, perfect, and move on. You want to draw attention to the fact that the condition actually is not met, but we still want to continue on with the problem. So the first one is L, linear. Does the data appear to show a linear relationship? Now, if the data doesn't show a linear relationship, then we wouldn't be performing linear regression on it, right? That makes sense, okay? So we would do like a non-linear regression on it. But this condition needs to be met in order to perform linear regression. So look at the scatter plot for this. And we say the scatter plot shows a moderately positive linear relationship, right? We can see the points increasing as we move across the graph in a linear pattern. Again, don't just rely on correlation for this. You can use correlation to support your description if you would like, but really just looking at the graph, you want to visually confirm that linear relationship. I is independence, right? Does the data represent an independent sample? So is the sample size less than 10% of the population? Again, this we usually just do in words, okay? And we state 15 is less than 10% of all school districts in the nation. That is a pretty safe assumption. So we're going to go on and continue with this and assume it's true. The next one is N, normal. Does a histogram of the residuals appear approximately normal? So we were given a histogram here, and unfortunately it does not appear approximately normal. It appears slightly right skewed with an extreme value. There is a visual outlier at about 8,000, between 6,000 and 8,000. So if we do have skewness or outliers, we want to draw attention to it, and the condition can still be satisfied if N is larger than 30. So if there's skewness or outliers, our condition still can be met, but unfortunately our N is, it said our N was 15. So because N is not greater than 30, this condition is not satisfied. So you see I kind of put down that as a commentary, and we draw attention to it. This condition is not satisfied. We still want to go on, check conditions, and actually construct the confidence interval. But in a 4-step process, if you ever run into this, please draw attention to it. Okay. Let's go on with our last 2 conditions. Does the residual plot show random scatter? So there's our residual plot again. Is there random scatter? Yes. Shows the residuals in a random scatter around the least squares regression line. That would be how you describe that. And then the last one, does the data come from a randomized experiment or a random sample? And it did tell us that the 15 districts were randomly selected. So everything that was in purple that we just went through is what you want to put down in your 4-step process. Okay. Now in class, I'm going to be asking you to do the 4-step process and to write down these conditions. Now on the AP exam, this usually takes longer than they would like, okay, because there's 5 conditions and you need a lot of information, as you just saw, to actually check these conditions. So on the AP exam, they won't ask you to check the conditions. They might ask you about the conditions in the multiple choice problems, or ask you to comment on one of the conditions in a free response problem. But they've come out and said, it just takes too long. We're not going to have you check all 5 conditions as part of the inference procedure on the AP exam. Okay. But we do want to know all the pieces of the conditions. And then, again, one of them was not met. We draw attention to it, but we're still going to go on and calculate. Now, to calculate, we want to make sure we state the inference procedure and then find our confidence interval. When we state the inference procedure on the AP exam, we can use words to describe it, or we can use our formula. So I put both of them down. Either or is good, but you definitely want to identify what your inference procedure is here. We are making a confidence interval for the population slope, and there is going to be our formula that we use. Now, we were given all of these values in some form in that beginning section. Okay, so here are all of those numbers repeated again. Now, some of these we might use, some of these we don't use. So it's up to you to kind of sift through what we need and maybe what we don't need. Okay, so first up, we need B. We need our point estimate, our slope. Now, I don't see B listed through any of these, but I am given our sample regression equation, which means that this is my y-intercept and this is my slope since it's the coefficient of x. So my B value here is going to be 0.4208. So that's what I'm going to substitute in for B. I'll calculate my t-star in a moment. I am given S. This is the standard deviation of my residuals. I am given S sub x, and I am given N. Okay. All of this other correlation, coefficient of determination at S sub y, it's just extra noise that you actually don't need to construct a confidence interval for. Okay. So I'm going to take and label all of those values again, because I'm eventually going to plug them into my confidence interval here. I do need my t-star value. So to calculate t-star, it's done the same as we've always done it. You just got to remember to subtract 2 for degrees of freedom. So our degrees of freedom are going to be 13 here. With a 95% confidence interval in your calculator, you do inverse t, 0.025 as your tail probability and 13 as your degrees of freedom. Okay, so just as a quick reminder, because we haven't talked about the t distribution in a moment. So 95% would be between negative t-star and positive t-star, which means that there is 2.5%, because it's symmetric, 2.5% in each of the tails. So if I do 0.025, that's this as a decimal, that's going to give me my negative t-star value for a 95% confidence interval. So I just make that positive for my t-star, since my confidence interval does plus minus t-star, right? We remember that, hopefully. So t-star is 2.16. So I have all my values. I can plug them into my formula. Okay, so I'm going to show all of those values substituted into my formula, and then I'm going to simplify. So if I simplify, this is my point estimate again, plus or minus, this is my margin of error now. Okay, my margin of error is 0.2688. So you can leave your confidence interval like that. There's absolutely nothing wrong with reporting your point estimate plus or minus your margin of error as your confidence interval. I always like making the confidence interval. So taking 0.4208, subtracting my margin of error to get this value, and then adding my margin of error to 0.4208 to get 0.69. Okay. So I calculated it. And then now I want to conclude in the context of the situation. So first I want to, interpret it, right? We are 95% confident that the true slope between average teacher salary and per pupil expenditure is between 0.152 and 0.69. Okay? So again, that is the true slope estimate. So those values represent the slope. Okay. This suggests a positive relationship, because remember the question asked us what kind of relationship this interval suggested. This suggests a positive relationship because our interval is positive. Okay? It covers positive slope values, so it suggests a positive relationship. I also wanted to conclude and say that because our normal residuals condition was not met, we should be careful with this interpretation because it might not be correct. And that's what we want to say if we do find that one of our conditions has not been met. We draw attention to it, we calculate, conclude, all of that. And then in part of that conclusion, we want to redraw attention to it and say that condition was not met, so this conclusion might be incorrect. Okay. And that wraps up Notes 1, Sampling Distributions and Confidence Intervals for Slopes. In the next video, Notes 2, we are going to start to go over hypothesis testing for slopes. So if you're ready for that video, go ahead and skip to Notes 2. I thank you so much for following along today. If you have enjoyed this video, please like this video and click subscribe to my YouTube channel for more great AP statistics content. Until then, I wish you endless statistical success, and I will see you in the next video.